Let me start with a question. You're training a neural network. You have a 16-core CPU. How many of those cores is Python actually using? Just one. That's the global interpreter lock, the GIL. Python's design prevents more than one thread from executing Python bytecode at the same time. All those cores sitting idle while your data preprocessing loop runs on a single thread. Now, let me show you what happens in Rust with the same workload. Picture a real training run. At any given moment, four things are happening at the same time. The data loader is reading the next batch from disk. The preprocessor is normalizing the current batch. The model is running a forward and backward pass on the previous batch. And a logging thread is writing metrics without interrupting any of the above. In Python, with the GIL, these tasks fight over a single CPU core. In Rust, they each get their own thread, communicate safely through channels, and synchronize precisely when they need to. Before we write any code, let's be precise about two terms that are often confused. Concurrency means multiple tasks make progress independently. They may not run at the exact same instant. They share computation time on one or more CPUs by interleaving. Think of a chef who starts the soup, then chops vegetables while the soup simmers, then comes back to stir. One person, multiple tasks in progress. Parallelism means multiple tasks execute simultaneously on separate processors. Different cores doing different work at the same physical instant. In a deep learning pipeline, both matter. Data loading is I/O bound. We want concurrency so the CPU is not blocked waiting for disk reads. Matrix multiplications are compute bound. We want parallelism, actual simultaneous execution on multiple cores. Rust handles both, and, critically, it handles both safely. We have three classic concurrency hazards. You need to know these because Rust's design is specifically shaped to prevent them. Race condition. Multiple threads access shared data without a defined order. The result depends on who gets there first. Non-deterministic, often catastrophic in AI, where corrupted training data gives you a model that looks fine but isn't. Deadlock. Thread A waits for B, B waits for C, C waits for A. Nobody moves. Your training job just hangs forever. Starvation. One thread monopolizes a resource and others never get access. Your evaluation thread never runs because training always holds the lock. In Python, all three can happen at runtime, silently. In safe Rust, race conditions are a compile time error. Deadlocks and starvation still require careful design, but Rust's primitives, channels and barrier, make the correct patterns natural to express. Let's write the first program. Rust's threading API is in the standard library. No dependencies needed. Run this and you might see main thread 1, main thread 2, etc. The spawned thread barely ran. Why? When main returns, all spawned threads are shut down immediately. The main thread's loop ran so fast, the OS never switched context to the spawned thread. Spawning the thread is not enough. If main exits first, spawned threads are killed. This causes silent data loss in a real pipeline. Now correct version. This version fixes the problem by calling join. A new thread is spawned and runs in parallel. The main thread also runs. Handle.join blocks until the spawned thread finishes. Result. All threads complete. No lost output. Deterministic termination. Imagine you are training an AI model. You have two jobs happening at the same time. One part prepares data, another part trains on that data. If you do this sequentially, everything is slow. You wait for data, then you train, then wait again. Not efficient. Now let's think differently. What if data preparation runs in parallel? While one part prepares the next batch, another part is already training on the previous one. This is exactly what's happening here. On one side, we have a data loader. It continuously prepares small chunks of data, batches. After preparing each batch, it sends it forward. There's a small delay, simulating disk or network I/O. On the other side, we have the trainer. It waits for incoming data. As soon as a batch arrives, it immediately starts processing it. This part is slower, simulating actual computation. So now you have a pipeline. Loader produces data, trainer consumes data, both run at the same time. No waiting, no blocking each other unnecessarily. The communication between them is done through a channel. Think of it like a conveyor belt. One side puts items on it, the other side picks them up. No shared memory, no locks, no complexity, just clean message passing. And here's something elegant. When the loader finishes its work, it simply disappears. That automatically tells the trainer there's no more data coming. The system shuts down cleanly, no special signals needed. This pattern is extremely powerful. You'll find it everywhere. Machine learning pipelines, streaming systems, game engines, even hardware design concepts. The key idea is simple. Don't share data between threads. Send data between threads. And this is where Rust really shines. It makes this pattern natural, safe, and predictable. No race conditions, no hidden bugs. Just structured concurrency done right. This is the same producer-consumer pipeline, but now it uses a structured data type instead of simple strings. What's new? A batch struct, ID arrow, identifies the batch data arrow input features, for example pixels. Labels to ground truth. The loader now sends realistic ML data, not just text. Vectors simulate images and labels. Each message is a full data package. The trainer receives a typed object, not raw data. Safer, clearer, closer to real ML pipelines. Key idea. You're no longer passing messages. You're passing structured data models between threads. This is how real systems work. Data loader arrow builds batches. Trainer arrow consumes batches. Clean, type-safe, and scalable. This program demonstrates a barrier synchronization pattern. What it does: spawns multiple threads, like attention heads in a transformer. Each thread, deposition independently, different durations, waits at a barrier. The barrier blocks each thread until all threads reach it. All threads must arrive, then all continue together. After the barrier, all threads are released at the same time. Now it's safe to combine the results. What is new here? Synchronization point, barrier. Unlike channels, data flow, this is about coordination. Ensures no thread moves forward too early. Mental model. Think of it like runners reaching a checkpoint. Nobody can continue until everyone arrives. Key idea. Use a barrier when work is done in parallel but must be aligned before next phase.